Welcome everybody to the Rocky Mountain Mathematical Physics Seminar. Our speaker today is Daniel Spiegel from the University of California at Davis, and he will speak about completely positive maps and the Stinespring theorem.
Thanks for the introduction, Marcus. I'm really happy to be back in Boulder, so also thank you so much for the invitation. Okay, so this will be an expository talk about a topic which is of interest to both, I think, quantum information theorists and operator algebraists. So I'm going to try and give both perspectives. So a more quantum information-y reference would be Nielsen and Chuang. That's a nice book to get started with the math of this stuff. And then Paulson is from an operator algebra perspective. Okay, so let me get started. We're used to, or I hope we're all familiar with, how density operators describe states in quantum mechanics and how those states evolve through the process of time evolution or measurement. So states are represented by density operators. Rho on a Hilbert space. Hilbert space H. And they evolve according to unitary evolution. Unitaries. So rho would go to U rho U star, or a U dagger, star or dagger, where U is in the unitary group of the Hilbert space. That would be some Hamiltonian time evolution. Or under measurement, we would act with a projection. So rho would go to P rho P over the trace of rho P, where P is a projection. So here the denominator, trace of rho P, is the probability that the measurement we do gives an outcome that corresponds to P. But I claim that it is practical and useful to sort of expand our notion of what sorts of operations we can do or evolutions we can do on density matrices. So the reason is the following. Suppose we have a bipartite system. Suppose that the total Hilbert space is in two pieces. And I have access, or I measure only observables that are supported on H1. So things that look like identity tensor H1. So this could be, for example, if my friend and I each have a qubit and I only have access to one qubit, or it could be that this is the system I'm interested in and this is some environment that could introduce noise or introduce noise to my measurements. Then how does the density matrix evolve? So if rho is the total density matrix, total state on H, then the state that I see by measuring H1, then is the partial trace of rho over system 0. So this is the partial trace which Connor introduced in his lecture last week over H0. So this is now a density matrix on H1. How does this evolve? So rho 1 for example, under a unitary evolution on rho, would go to a partial trace of u rho u star. Okay, but while this is a unitary evolution of rho, it is not a unitary evolution of rho 1. So what I see by just looking at H1 does not look like a unitary evolution or a measurement even. So I need to expand my notion of what kinds of operations I can do on states. Now, there's another problem, which is that this is not even a well-defined function of rho 1, because rho is not a function of rho 1. Rho 1 is a function of rho by this formula. So let's assume, just so that we have a well-defined function, that we're initially in a product state. That initially rho is of the form rho tensor rho 1 for some fixed rho naught. Rho naught would then be a density matrix on H naught. So now rho 1, the evolution of rho 1, it looks something like this. And maybe there's a measurement involved as well. This is now a well-defined function of rho 1, and I want to understand what kind of object is this mathematically. Okay, so the moves that I'm allowed to do are tensoring on fixed non-interacting qubits or qubits or whatever kind of system. I can do unitary evolutions, I can do measurements, and I can trace out degrees of freedom. So I claim that the following definition is the right one. I'm going to have to explain what this definition means. So we're going to let H1 and H2 be finite dimensional Hilbert spaces. Finite dimensional. So a quantum operation is a linear map, which I'll call capital phi, from H1 or from bounded operators on H1, or just linear operators since we're finite dimensional. Bounded operators on H2, which is, I want it to be trace decreasing on positive operators. So a trace of phi of rho is less than or equal to trace of rho. And I want it to be completely positive. And I'll say what completely positive means. Be defined. Now you would think you might complain that I should be trace preserving if I want to map density matrices to density matrices, because density matrices have to have trace 1. But I want to be able to talk about measurements. That evolution of rho under a measurement is not linear. So to get to something linear, I have to just take the numerator. And when I just take the numerator, I'm now trace decreasing rather than trace preserving. So we're going to allow ourselves to have trace decreasing when there's a measurement. Right. And this will just be like conjugation by a p without the denominator. Okay, what is completely positive? So let's make another definition. So completely positive maps are of interest, as I said at the start, to operator algebraists and to quantum information theorists. So I'm going to give you this from the operator algebraist perspective. Well, I mean, they're the same perspective, but let A, I'm going to give it a little bit more general. So let A and B be C-star algebras. So I just want to generalize to C-star algebras rather than V of H. So a map phi from A to B is completely positive, or just CP, if the following map, the tensor product of phi with the identity map, so this is now a map from the tensor product of A and MNC, the n by n matrix algebra, to B tensor MNC. I want to require that this map is positive. So positive means that I map positive elements to positive elements. Positive is a well-defined notion on C-star algebras. This tensor product, this is the algebraic tensor product, but it has a unique norm that makes it into a C-star algebra. So this is now a map between C-star algebras, and I want it to be positive. Okay, why is this something that I care about? Why is it not good enough to just require quantum operations to be positive?
Good question. What is in? Is that for all n?
Yes, if it's positive, yes, thank you. For all n. Let's say we have a three-part system. So we have H, which is equal to H naught, tensor H1, tensor H2. If I evolve the state, so if I have so H1, so I want to say initial state so H naught here is still the environment, but H1 and H2 are allowed to be entangled. So I might have access to H1 and somebody else has access to H1 and H2, or I have access to both. But if I now do an operation that's just on H0 and H1, so if I have phi of rho, which is like trace of, let me do it one thing. So if I have a quantum operation on H1, which is phi of rho is equal to trace over 0 of u star rho naught tensor rho, like we've had before. The star should go on the other side. Well, I can still tensor product rho naught onto H1 and H2. I can still evolve with this unitary, and I can still trace out the 0 component. So I can still look at this operation as an operation on H1 tensor H2. So this would be the operation that takes rho to tracing out H naught, but now I have to tensor with the identity. So this is how an entangled state This would be H1 or H2. This is how an entangled state would evolve. Here, U is supported on site 0 and 1. I is only on H2. This rho naught is only on H0, and this rho is on H1 and H2. This is exactly phi tensor identity on, well, the dimension of H2 applied to it. So the point is that allowing completely positive maps in our definition allows us to consider states which are entangled with a third system and still get valid operations. Okay.
And the other example of positive.
Yeah, absolutely. Right here. So transpose is positive, but not. So this would be like A, B, C, D maps to A, B, C, D. This is an example on right. I be a little bit more clear. Let me leave it at that. This is an example, and I can give a little bit more details after the talk if you want. Okay. So let's give some examples of maps which are completely positive.
Well, another kind of companion question.
Yeah.
Is M and C like kind of special in the realm of C-star algebras?
Yeah.
What makes it special?
Well, it's finite dimension, and it's simple. Every finite dimensional simple C-star algebra is M and C for some n. And it's also special because this tensor product has a unique C-star norm on it without having to even complete it. So this has a norm on it that makes it into a C-star algebra. There's no completion involved. It's already complete. So that makes it special. Okay, so it's examples of maps that are completely positive. So proposition. If phi is a star homomorphism, then phi is completely positive. Why? Because when you tensor phi with phi tensor, when you do phi tensor identity, you still have a star homomorphism. And star homomorphisms map positive elements to positive elements. Because phi of A star A, here's a positive, generic positive element. That's phi of A star phi of A, which is another generic positive element. Okay, so star homomorphisms map positive elements to positive elements. Therefore, they're completely positive. Here's another. If H and K are Hilbert spaces, and we have a bounded linear operator, let's call it B, from H to K. Then conjugating by B gives me a bounded linear operator. So, or it gives me a completely positive map. So A here is going to be, wait, I want this to go B star. And this is completely positive. And just to sketch the proof, phi tensor the identity. This is now B tensor the identity. Conjugation by B tensor the identity. So this is A, and this is B tensor the identity star for all A in B of H tensor MNC. Now, this is an element in, so this is an element of B of K tensor MNC, which is precisely the bounded operators on K tensor C to the n. And when I conjugate a positive operator, I still get a positive operator, because what happens to the expectation values? The expectation value of this operator for any x in this Hilbert space is positive. Okay.
Wait, sorry, where does A live in?
A lives in bounded operators on H tensor MNC.
Sorry, in the first.
In the first one, A lives in B of H.
Yeah. Okay, and 5A lives in B of K.
5A lives in B of K. Yeah. So B star goes from K to H. So this goes K to H, A goes H to H, and then B goes H to K. Okay, the point is just that I have two very nice examples of completely positive maps, one being star homomorphisms, and one being conjugation by arbitrary bounded operators. Let me.
Sorry, also where did bounded come in? Just so I know how it differs from 5 dimensions.
That in finite dimensions, every linear operator is bounded.
Yeah. So
But in
what is the assumption of bounded?
because I want to see star algebra.
I see.
Right, you need that domain. Yes. One more easy proposition. That compositions CP maps CP and sums of CP maps CP and positive scalar multiples. CP maps. Okay, so let's think back to our original quantum operations that we were allowed to do. We were allowed to tensor on fixed density matrices. We were allowed to conjugate by unitaries. We were allowed to conjugate by projections. And we wanted to trace out degrees of freedom. Okay, well, conjugation by unitaries and projections, we've already shown, is completely positive. What about the other two? So, I'll say, but rho naught be a fixed density operator. H1 or H0. So then I claim that rho 1 mapping to rho naught tensor rho 1 is CP. The proof is very simple using the formalism of partial bras and partial cats that Connor introduced last week. So the proof, I write rho naught as its spectral decomposition. So this is like Ti, I equals 1 to n for some n. Right, these are the eigenvalues, an orthonormal basis of eigenvalues of rho naught. These are these i's are an orthonormal basis of eigenvectors of rho naught. These Ti's are the corresponding eigenvalues. So these Ti's are positive, and they sum to 1. Now this map can be written in terms of partial bras and partial cats. So rho 1, or I should say rho naught tensor rho 1 is exactly the sum from I equals 1 to n of Ti I rho 1 I, where these i's are now partial bras and partial cats. So I could put a little subscript if you want, which say that they're living on H0. So this is a map from H0 tensor H1 to H1. This is a map from H1 to H1. This is a map from H1 to H0 tensor H1. And this is the conjugate of that. So this thing is completely positive by that proposition. And I've summed up a bunch of completely positive maps. Let's look at the partial trace. So I claim that rho mapping to trace of rho naught is CP. And again, this is extremely trivial using the formalism of partial bras and partial cats, because trace over 0 of rho is equal to sum I partial rho I 0. But this is the partial cat, this is the partial bra. And since this is a conjugate of that, again, it's completely positive. So all the types of operations that I set out to understand are completely positive. Can I go the other way? Is every completely positive map, in some sense, a valid quantum operation of the kind above that we're trying to understand? So this is where Stinespring's theorem comes in. Stinespring's theorem is a very powerful tool for understanding completely positive maps. And from my experience, the C-star algebraists and the quantum information theorists talk about Stinespring's theorem in different language. So I want to try and resolve those two different approaches.
Stinespring computation.
I think you were mathematician. Yeah. Okay. So the theorem. This is Stinespring's theorem. Let A be a unitary algebra. H a Hilbert space. And phi from A to P of H. Stinespring's theorem tells us that we can decompose this into the two types of completely positive maps that we know and love. So there exists, the theorem is that there exists a Hilbert space K and a unitary star homomorphism, so called pi, from A to B of K, and a bounded operator B from H to K, such that phi of A equals, first I apply pi, and then I apply B. For all A. Okay. Let me make sure I got this right. So V goes from H to K. Yes, pi of A goes from K to K. E star goes from K to H. Okay. And we say K pi B is called Stinespring representation. There are special kinds of Stinespring representations that I want to use called minimal Stinespring representation. So a Stinespring rep K pi B is minimal if, let's see, right. I have A, H, span of this. Okay, so pi of A VH means the set of all elements of the form, well, pi of A V and applied to an element of H. This is called minimal because it means that K is not too big. K is sort of just as big as it has to be. Okay. Now, these always exist. And in fact, they're unique up to unitary equivalence in some sense. Okay. So I want to use this to say that completely positive maps look like partial traces and conjugations by unitaries and projections and tensor non extra density matrices. And the way I'm going to prove that is by passing to a different representation. So passing to a different form of completely positive maps. And we're going to have to restrict ourselves to finite dimensional Hilbert spaces at this point. Theorem. If H and K are finite dimensional, and phi is CP, phi from B of H to B of K. CP. Then there exist operators E1 up to EK, which go from H to K. Such that K is less than or equal to the dimension of H times the dimension of K. And phi of A is the sum, I equals 1 to K, of EI, A, EI. And now I have to make sure I put the star in the right place. This had better go from K to K. So I want a star here. Okay. So this writes our completely positive map as a sum of conjugations. What's the proof? We're going to take a minimal Stinespring representation. Fine. Pi. Okay, so we observe now that K is equal to the span of pi of B of H V K. Oh, I need a new letter. Let's call this L. Good. B K. And the dimension of this, well, B of H has dimension of H squared. So the dimension of L is therefore less than or equal to dimension of H squared times the dimension K. Okay. Pi is a map from B of H to B of L and is a unital star homomorphism. Now, unital star homomorphisms between finite dimensional simple C-star algebras have a very nice form. In particular, we know from this that the dimension of H divides the dimension of L. And there exists a unitary U from L to H tensor C dim L over dim H, such that, slightly running out of space, I of A has the following form. I of A is simply A tensor the identity up to a unitary conjugation. So this is U there, and this is U star. So this unital star homomorphism essentially looks like tensoring on the identity operator. Okay. Now I can define the EI operators. We're gonna let 1 to k be an orthonormal basis for C to the dim L over dim k. Then I can write phi of A first using my Stinespring representation. E star pi of A V. Then using my explicit form for pi of A. Then I can write I in terms of these basis vectors. On to the dimension. Okay. I realized that I should have called this, saved myself some chalk. So this is up to k. So I insert a resolution of the identity like that, and then I write this in terms of partial bras and partial cats. So this is the sum from I equals 1 to k, B star, U star, the partial cat, A, partial bra, U, B. And this is EI. Okay, that's what we wanted to do, because k is less than or equal to the dimension of, oh, did I swap H for K? I think I swapped H for K at some point. Yes, exactly. Okay, it was dimension of H up there. That should be good. Dimension of H, dimension of K. Okay, so we have proven the theorem. Now, this theorem did not need to be proven with Stinespring's theorem and minimal Stinespring's theorem, minimal Stinespring representations as presented here. This theorem can be proven with just linear algebra without ever saying the word C star algebra or Stinespring, but you know, this is the connection. It feels a little bit like killing a spider with a flamethrower, but it works. Okay. We're still not where we wanted to be. This is called the operator sum representation, right? This EIA, EI star sum is called the operator sum representation for your completely positive map. I think I won't have time to prove it, but we can now use that operator sum representation to show the following theorem. So if H and K are as before, so H, K, phi as before, there exists there exists a Hilbert space. Let me make sure I get all the data. Wait. So for any phi naught in K, or for any unit vector, and a unit vector E naught in C to the K plus 1, there exists a unitary. There exists unitary U on H tensor K tensor C to the little K plus 1, and a projection P on H tensor K tensor C to the K plus 1, such that phi of A is exactly what we want, is exactly the kind of operation that we've set out to describe. So this is on H tensor C to the K plus 1. I'm going to trace over that. I'm going to do a projection, my unitary A tensor phi naught E naught U star. So, given some completely positive map from B of H to B of K, there exists some auxiliary Hilbert space such that, and unitary and projection, such that this completely positive map phi is exactly the composition of tensoring on a fixed identity matrix, conjugating by a unitary, conjugating by a projection, and then tracing out the unwanted degrees of freedom. Okay, I think my time is pretty much up, so I'm going to stop there. Fortunately, I didn't get to the proof, but I hope you agree that this is an extremely beautiful mathematical framework for something describing something very useful.
Yeah, thank you. Other questions? Either from here or from the external audience, so. Yeah.
So
yes.
is the utility of this result the fact that we're now able to use this representation more easily in computations, or?
Yes, yeah, right. Like each of these, so when we have this abstract mathematical concept of completely positive, that might be useful for proving theorems. Then we have two very nice, computational representations that each have their own strengths.
Quick question, actually. So you may want to formulate this in principle for maps from A to A instead of A to B of H. I was thinking you can also do this.
So I would take, right, I would first take a faithful representation,
Oh, sure.
and then it becomes a map from A to B of H.
Okay, then I guess H, might not be finite dimensional.
No, the H there need not be finite dimensional.
Okay, and that was fine for what followed.
So the H in Stinespring's theorem need not be finite dimensional.
Right.
For this Krauss, so these EIs are called Krauss operators. For that representation, I think we do need finite dimensionality.
Okay, right, to get a sum, I guess.
Yeah, to get a sum.
Okay, and you didn't need separability of H?
No, I don't need separability of H.
Thanks.
Okay, let's thank the speaker again. So, if I'm informed correctly, next week, Howie Jordan will speak about certifications of spaces of density matrices. Okay, thank you. Then, thank you, everybody, and see you next week.
Who's giving the talk after Howard?